Okay, so good afternoon to all the dear participants, and thank you for allowing me coming in this session. Hey, is my voice audible to all of you? I'd like to ask you that is my voice audible to all of you?
Yes, it's audible.
Today, in this session, I'll be taking the session actually, and in this session, I'll be discussing about uh, different aspects of electric vehicle actually. First of all, so this is whether this PPT is shared or not. Okay, wait, just 1 second. So allow me to share the PPT first, and then after I'll be okay. The PPT is visible, right? Okay. So so uh, in this part, as you all know that that the number of electric vehicle is increasing day by day, as because the whole environment is getting polluted day by day due to the rapid, rapid, burning of fossil fuels, and moreover, the fossil fuel is getting extinct nowadays. Okay, so that's why the use of electric vehicle nowadays is a major concern. Really, okay. Globally, the road condition is getting busier day by day by with increasing number of transportation mediums like the buses, car, heavyweight, and medium weight electric vehicle. And a study says that about 19% of the pollution is contributed to the transportation section, really. Okay, so this whole transportation section contributes to about 19% of the pollution, actually. So that's why it's our duty to use a vehicle which will not pollute the whole environment. Okay, so whenever so uh, so So that's the reason why electric vehicle has found its potential application. There are mainly 3-4 types of electric vehicles being used. Electric vehicles, the plug-in vehicle, plug-in hybrid electric vehicle, and then your have your plug-in hybrid electric vehicle, and then you have your fuel cell hybrid electric vehicle, and then you have your hybrid electric vehicle actually. So there are different types of electric vehicles available in the market. Now, uh, previously, Professor Kumar Shankar actually said in his session, okay, that I feel that that part is a little bit wrong. Yeah, I feel so because he said that the road condition is given wise actually, but the truth is that countries cycle. India, we have our own drive cycle, own drive cycle, and more. This graph is based on uh, this type of thing. So basically, life cycle is a representation of of different types of areas. So means this table actually depicts the life cycle. Shows that 81 vehicles do inactive. This means I'm not going into details of this type of things actually. So to means this block diagram describe different types of forces acting on an electric vehicle. Resistance force, the gravity force, okay. acts on, and depending on this type of forces, the vehicular shape is basically modified. This under aerodynamic electric. Fine. So this also is not our major point of concern. This table is basically the specification of a medium weight electric vehicle, which says that the mass of an electric vehicle, mass of a medium weight electric vehicle, nearly is 540 kg, where the weight of the payload is 280 kg. This 280 kg comes because, see, medium electric vehicle means this is your, sorry, this specification is a specification of light electric vehicle. Okay, now. Yeah, and the car means the the passenger to have a weight of 80 kg. That means 80 into 4 20 kg. So means what? And is being by AERI organization of, okay, and they say weight load normal condition is 280 kg. The of a lightweight, so the present. So the we are having SRM type of machine, means switch reluctance machine. We are having induction machine. We are having means this type of this 4 or 5 types of machine are normally used electric vehicle. So what? So depending on what things actually the motors are selected, like the motor vehicle have a high torque to inertia ratio as well as a very high to weight ratio. Likewise, the motor used in an electric vehicle must have in acceleration. Part of the electric vehicle must have. Okay, my voice is audible or not? Hello.
Sir, it is not audible. It is very disrupting.
Okay, it's very distracting. Okay, just wait. Just wait for a second. Just wait for a second. Oh. नेट ठीक है चाहिए नेट now is the voice audible? Now it is clear. Now is the voice clear now?
So your voice is clear, but whatever you start speaking, it comes in spurts. It is not coming with a continuous thing. Giving in spurts. That is what problem when you start speaking in a lecture. Otherwise, it's clear. When you ask, it is clear.
Okay, so let me again start it, and let's see what happens actually. Okay, just wait for a second. Whether I'm trying to speak in a microphone. I feel through microphone the voice will not. Now is it okay? wait for some time. Okay, now is my voice coming now?
Yes, yes.
Okay, I feel it's okay now. Okay, so let me share the presentation. Where it is.
No.
Okay, now is the presentation coming? I feel it's coming, no?
Yes, sir, it is
Okay.
received now.
Yes.
So the thing is that, so this is the characteristic, means this slide shows the characteristic of, means what are the different characteristics which an electric propulsion machine must have. The first and foremost one is that it must have a high torque to inertia ratio as well as a high power to weight ratio. It must also have a very high magnitude of maximum torque capability during acceleration, as well as the motor used in electric vehicle must have a high starting torque. Okay, why this is required? Because means it's not possible for the passenger to ride in an electric vehicle which is already in a running mode. So means what? First, your vehicle must be stopped, and thereafter it must load its payload, and thereafter the vector means the electric vehicle must start itself. Okay, that's so that is the reason why electric vehicle requires a high amount of starting torque actually. Okay, now moreover the size so moreover it must have low weight, because if it has a huge weight then it will create, if suppose the body of the electric vehicle is very heavy, then it will create a huge load for the motor, and thereby the motor will not be able to sustain. Okay, now moreover it must have high efficiency over low and high speed range, and moreover it mustn't have minimal amount of torque pulsation, because if suppose there's a pulsating torque, the drivers along with the passengers of the electric vehicle will experience sudden jerks actually, and it will not be it will just be like a roller coaster ride for the passengers who will be uh, traveling in the electric vehicle. So that's why the torque fluctuation or the torque pulsation must be very much low. So in this presentation, I'll be mainly focusing on few aspects. The first and foremost aspect is that what is torque pulsation, how it gets occurred, and thereafter I'll be discussing about different control topologies which are normally used in means different control topologies of the electric motors which has which are being used in electric vehicles. So let's come to the first part, that is your torque pulsation. These things you have already learned because Devasys sir and many other teachers have already discussed that what are the different types of motors are being used. So these things I'm not going into. I'm straightforward moving into the part which is known as the torque pulsation. Okay, now. So before that, I feel you have idea about the modeling of an induction machine. So this is your D and Q axis equivalent circuit diagram of an induction machine. Fine now. So this is the equivalent circuit diagram. Now see, torque pulsation, one of the main aspects which is present in an induction machine, and we need to reduce. Basically, the torque in any kind of machine are of two types. The first one is known as the steady state torque, and the second one is known as the pulsating torque. How does the steady state torque get produced? Steady state torque is produced by the interaction of the fundamental flux with the fundamental current with each other. Steady state torque is produced by the interaction of the fundamental flux with the fundamental current. And the pulsating torque is getting produced due to the interaction of the harmonic current with the fundamental flux or fundamental flux with the harmonic current. Okay, now what is this fundamental flux, harmonic current, and all those things? Now I'll be discussing about actually. So this is the equivalent circuit of an induction machine, the fundamental equivalent circuit of an induction machine. Okay, So where LS is the stator side inductance, RS is the stator side resistance, LR is the rotor side inductance, and RR by S, where S is the slip actually. Okay, it depends. S is equal to what? NS minus NR divided by NS. Okay, now so slip can vary from 0 to 1. When the machine it has standstill, you can say NR is equal to 0. That means what? The slip is equal to 1, and when the machine means the rotational speed of the machine reaches to that of the synchronous speed, the slip will be equal to 0, isn't it? So that's it. So means what? This is the fundamental equivalent circuit of the machine. Now, if suppose the machine is fed by a voltage equal to the magnitude of the nth order harmonic voltage, this is the Vn. This Vn is the magnitude of the nth order harmonic voltage. The whole circuit will just be simplified as if it looks like this one. Why it happens? This is the harmonic equivalent circuit. This is the harmonic equivalent circuit of an induction machine. Why? Because the slip for the fundamental is normally very low, isn't it? So you can say if the slip is very low, you can say that RR by S is very high. This one. If the slip is very low, then you can say if the slip is very low, then you can say RR by S is very high. For example, if you take the slip is equal to 0.02, or might be the slip is equal to 0.03, so you can say the RR by S quantity, this quantity becomes very high. Okay, but for harmonic component, the slip normally is equal to 1. For harmonic component, you know it very well, the slip becomes equal to 1. So you can say RR by S, this means slip is very low for the fundamental component. It is in the range of 0.01 or might be 0.02, 0.03 like this. But for the harmonic component, the slip normally is very high. And thereby you can say if the slip is very high, that means what? S nearly tends to 1. Then you can say that RR by S is basically equal to RR. Okay, so the RR means the rotor resistance. The rotor resistance for an induction machine normally is very small quantity. It is negligible. Okay, so you can say if the S is very high, nearly closing to 1, you can say RR by S will be equal to RR, and moreover, in an induction machine, the RR tends to means it's a very small quantity, it's a negligible quantity. So you can say the RR by S, this whole quantity can be avoided in harmonic component. But whereas you are trying to find out the fundamental component, the slip normally is very low. For the fundamental, the slip is low, but for the harmonic component, the slip is normally very high. And that's the reason why this is your fundamental equivalent circuit and this is your harmonic equivalent circuit, where the RR by S quantity is normally neglected. Fine. So in the harmonic equivalent circuit, you can see that this whole quantity, if the RR by S is neglected, that means what? It can be represented as a short circuit. The whole thing, this thing gets omitted. So you can say that LR by LM means your magnetizing inductance, and the LR is your rotor inductance, rotor side inductance. These two gets in parallel with each other, isn't it? So you can say this LR and LM becomes parallel with each other. And normally for an induction machine, you know, LR is a very small quantity, so it will dominate. So if these two things are in parallel with each other, so you can say LR will dominate over LM. Okay. Moreover, at a high frequency, so means what? This LM can be neglected. This LM can be neglected. You can neglect this one, and moreover, when you neglect this one, this LR becomes in parallel with the LM, and thereby you can say that this ALR in an induction machine, as because it is a very small quantity, and these two are in parallel with each other, so you can say this ALR becomes dominant with respect to ALM. Fine. So this part is clear now. Now, what about the RS? In the harmonic equivalent circuit, the RS is not taken actually. See here, there is no RS. There is no RR by S. That is true, okay, because the S is very small actually. That's why the RR by S will be negligible. Moreover, as because the LR is comparatively very small as compared to the LM in case of an induction machine, so you can say, and these two are in parallel, so you can say that the LR and the LR will be dominating over the LM. So this part is getting constructed. Now, at high frequency, as the LS dominates over RS, at high frequency, the LS will dominate over RS. Okay, so the motor will be seen as a sum of two leakage inductance in harmonic equivalent circuit, just like this one. See, the motor is being seen as a series combination of two leakage inductances. One leakage inductance is LS and the other leakage inductance is LR. Fine, now? So thereby you can say that the expression for the nth order harmonic, the amplitude of the nth order harmonic current, if you represent it as In, that is equal to Vn divided by n omega multiplied by Ls plus Lr, isn't it? Isn't it? Because it is equal to Vn by Zn actually. And Zn is nothing but n omega Ls plus Lr. That's it. Okay, now. So the expression of the In will be equal to Vn divided by n omega Ls plus Lr. That's it. Okay, now. Why? Because this is the harmonic equivalent circuit of an induction machine. Likewise, if you use synchronous machine or something like that, you can easily find out the harmonic equivalent circuit. And why this circuit is being derived? Because we want to find out the torque pulsation, and you know the pulsating torque is getting produced due to the interaction of the harmonic current with the fundamental flux, of the fundamental current with the harmonic flux. That's it. Okay, now, so you need to know about the harmonic equivalent circuit. Now, you know that this is a three-phase induction machine, and this one is the per-phase fundamental equivalent circuit of an induction machine. So you can say the expression of the VRN1 is equal to Vm sine omega t if you take. And you know that the three phases are phased apart by an angle of 120 degrees. So you can say VRN1 means your fundamental component. VRN1 is equal to Vm sine omega t. VYN1 is equal to Vm sine omega t minus 120 degree, and VBN1 is equal to Vm sine omega t plus 120 degree, isn't it? Now here you can see that the expression of the VRN1 is equal to, you can say it in this fashion also, IR1 into RS plus of D phi R1. Now, what is this RS? Okay, what is this IR1? Now, see, this quantity IR1 into RS, or might be IY1 into RS, or might be IB1 into RS, all these three quantities are negligible. Why negligible? These three quantities are negligible for high speed and high modulation index. Why? Because IR1 into RS is a drop which is very negligible for a high speed application. IR1 is the fundamental component of the R phase current. IY1 is the fundamental component of the Y phase current, and IB1 is the fundamental component of the B phase current. Right? Okay, so you can I into RS is the stator resistance drop, and for the high speed application, these quantities can be assumed to be zero. So you can see the amplitude of the VRN means here VRN1 is nearly equal to d phi by dt. You know it very well. Okay, now This is just like the V by F control. For the V by F control, you have seen that the induction machine basically have three types of control topologies. One is your scalar control. There's two type of control topology. One is your scalar control, and second one is a vector control. Right? The scalar control is nothing but V by F control, and the vector control is something different. Actually, I'll be discussing about those type of control topologies. Now, the vector, now this V by F control is very simple actually, but still people are much more compatible with the vector control. Why? Because the scalar control or the V by F control is not suitable for low speed application. For V by F control in low speed results into what? Flux weakening mode. You must have learned this thing actually. What is this field weakening mode of control and those things? Okay, so for because for the low speed, the V by F control, results into flux weakening. So for the low speed, certain boost converters are being used. That's the main reason why the V by F control is not being used often today. Okay, but this vector control is applicable for high speed, low speed, and medium speed, all the speed ranges. That's why this vector control is so much used in case of induction machine applications. Right now, see why. So you can say Vrn1 is equal to d phi r1 by dt. Vyn1 is equal to d phi y1 by dt, and Vbn1 is equal to d. You know these things, okay? Now you have already derived Vrn1. Vrn1 is equal to what? Vrn1 is equal to V1, or you can say Vm into sine omega t. And so likewise, you can derive for the Vrn5. 5, it will be what? 5. In place of 7, it will be 5 actually. It will be V5 into sine 5 omega t. Okay. Likewise, Vyn5 is equal to V5 into sine of 5 omega t minus of 5 into 120 degree. 5 into 120 degree, 5 into 120 degree, most probably, I don't know how much it will be, but this thing will be equal to V5, Vyn5 will be equal to V5 into sine of 5 omega t plus 120 degree. And here, if you try to find out the Vbn5, it will be equal to V5 into sine of 5 omega t minus 120 degree. That means what? That signifies that the fifth harmonic component, V5 is the fifth harmonic component. So here you can see that there is a clear case of phase sequence reverse for the fifth harmonic component. For the fifth harmonic component, the phase sequence is getting reversed. Okay, so the fifth harmonic voltage produces a magnetic field which makes the motor rotate in the reverse direction, right? Because the phase sequence, you know, Vrn1 is equal to V1 into sine of omega t. Vyn1 is equal to V1 into sine of omega t minus 120 degree, and Vbn1 is equal to V1 into sine of omega t plus 120 degree. But if you try to find out Vrn5, then it will be V5 into sine of 5 omega t. Vyn5 will be equal to V5 into sine of 5 omega t plus 120 degree. Here it will be plus. Now you see, so you can say that the fifth harmonic voltage produces a magnetic field which makes the machine rotate in the reverse direction, and that also in reverse direction with respect to the fundamental, you can say. If the fundamental rotates in anti-clockwise direction with the speed of omega, the fifth harmonic voltage will rotate in the clockwise direction with the speed of 5 omega. That's it. Now, if you find out the VR, what is the amplitude of the seventh harmonic voltage? See, the third harmonic will not be present, because you know that if you are using a three-phase induction machine, that means what? For three-phase connection, the triplet order odd harmonics gets omitted by default. Okay, that means for the third harmonic, ninth harmonic, 15th harmonic means the multiple of 3, all those harmonics will not be present over here. Fine. Now the amplitude means the expression of the 7th harmonic voltage VRN7. See here, VRN7 is equal to V7. It will be V7 into sine of 7 omega t. VYN7 is basically equal to V7 into sine of 7 omega t minus 120 degree, and VBN7 is equal to V7 into sine of 7 omega t plus 120 degree. And this phase sequence is same as that of the PRN1, means the fundamental. This phase sequence of the 7th harmonic voltage is same as that of the fundamental. You can see here. That means what? The 7th harmonic component will produce a voltage. Means so the 7th harmonic voltage produces a magnetic flux which makes the motor rotate in the same direction of that of the fundamental. Right? And but here the rotational speed of the 7th harmonic flux will be equal to 7 omega. Okay, so see, just go to this diagram. You can see that if this is your R phase, this is your Y phase, and this is your B phase, which are being phased apart by an angle of 120 degree, so you can say that the fundamental, if suppose it rotates with the speed of omega, the fundamental flux phi1, and suppose it rotates in the clockwise, anti-clockwise direction, so you can say the 5th harmonic means your phi5 rotates in the clockwise direction with a speed of 5 omega, and your 7th harmonic flux component, that is the phi7, rotates with the same direction to that of the fundamental, but it is having a speed of 7 omega. Right? Okay. So you can say that the relative speed, so you can say from this diagram that the relative speed of the 5th harmonic magnetic field with respect to the fundamental is equal to 6 omega. Because see, here the fundamental rotates with omega and the 5th harmonic rotates with 5 omega. So if you try to find out the relative speed, as because these two components rotates in the rotates in the opposite direction to each other, so you can say that the relative speed between these two components is equal to 6 omega. Okay, so that causes your 6th harmonic torque. That is the main reason of creation of 6th harmonic torque, right? That is the main reason of creation of 6th harmonic torque. Likewise, if you try to find out the relative speed between the fundamental and the 7th harmonic, here also you'll see that the relative speed between these two, in the fundamental and the 7th, is also equal to 7 omega. So interaction of the fundamental flux with the 7th harmonic current will also produce 6th harmonic, because the order of the harmonic depends upon the speed of the harmonic torque component. Actually, as because the speed is 6 omega, so that's why this torque is named as 6th harmonic, right? So in general, so you can generalize the whole thing and say that 6k minus 1 order harmonics produces magnetic field revolving in the other direction while the other moves in the same direction. Right? So this is the main thing actually. So so you can say that the production of the pulsating torque can be of 3 types. There can be 3 main reasons of the production of the pulsating torque. The first reason is the interaction of the fundamental flux with the harmonic current. The second reason can be the interaction of the fundamental flux, interaction of the fundamental current with the harmonic fluxes. Or the third point, the third will also cause pulsating torque. The third point is that interaction of harmonic flux and the harmonic current can also produce pulsating torque, but the third option will produce pulsating torque. That is true, but it will be very weak in nature. It will be very weaker in nature. So mainly the strong pulsating torque is getting produced due to the interaction of the fundamental flux with the harmonic. Okay, the pulsating torque gets produced with the interaction of the fundamental flux with the harmonic current. And moreover, the harmonic torque will be of the order of 6th order harmonic torque, 12th order harmonic torque, 18th order harmonic torque, 24th order harmonic torque. But there cannot be any torque like 5th order pulsating torque. No, it cannot be. 7th order pulsating torque. No, it cannot be. Okay. The pulsating torque will be of order of 6, 12, 18, 24, and all these things. Okay, now? So this is the reason, this is why the pulsating torque is getting produced. What Debasis has told in his lecture, actually, he has discussed a little bit about the pulsating torque, and I have tried to discuss in details about this pulsating torque nature. So now the next point is a selective elimination. So now the main thing is that we don't want this pulsating torque. We want only the steady torque. Okay, now so you can see that the 6th harmonic torque here you can see I have told that pulsating torque is produced due to the interaction of the means mainly produced due to the interaction of the fundamental flux with the harmonic current. See here, this is the fundamental flux phi1 with the harmonic current. What are the harmonic currents which are responsible for production of the 6th harmonic torque? 5th and 7th. Both of them produce your torque pulsation, right? So you can see that tau 6 means T6, okay, means the 6th harmonic torque component is basically equal to phi1, means is directly proportional to phi1 into V5 by 5. Now see here, I5 is basically V5 by 5. You know it very well because you know that because in the beginning only I have told you that In is equal to Vn divided by N omega into Ls plus of L. N omega, I'm saying, where N is the harmonic component, harmonic order. So N, so for the 5th harmonic current, the N is represented is replaced by 5 actually. So you can say that the I5 is equal to V5 by 5 and I7 is equal to V7 by 7 actually. It will be 7 omega actually. It will be okay. So omega is common, so that's why you can neglect. So you can see that the torque, the 6th harmonic torque, is directly proportional to the phi1 multiplied by V5 by 5 minus of V7 by 7, where V5 is the amplitude of the 5th harmonic voltage and V7 is the amplitude of the 7th harmonic voltage, right? Okay. So these are the things actually. So I'm taking a little, okay, is my voice clear?
Yes, sir.
So I'm taking a 2 minutes break right now. Okay, I'll be joining now only. Okay. Mute. So welcome back again. So actually, the thing was that this presentation were not been planned actually at the initial stage. I didn't plan to give any presentation. All of these things were being made in 1 hour actually. I'm trying to present whatever knowledge I'm having about electric vehicle and all, and means whatever research I'm doing on this particular field. Okay, so these are the main topics. Means my presentation, I'll be focusing on what are the different causes why electric vehicle the torque pulsation is getting produced, and what are the different control topologies of a machine actually. Fine. So these are the things actually. Okay. So now, so these are the torque pulsation. These are the main production, means the main creation of torque pulsation, and the torque pulsation can be eliminated by the use of different sort of PWM techniques. Right? Nowadays, people are going for the space vector PWM, advanced type of space vector PWM, isn't it? Advanced type of space vector PWM means what? See, in space vector PWM, we know that in conventional space vector PWM, we basically use 0127 sequence. Okay, now suppose you have a three-phase inverter, you know this myself. Okay, 0127. 0 means what? Plus, sorry, minus, minus, minus. 7 means plus, plus, plus. Means what? Suppose you have a three-phase inverter. In the slide, I don't have the three-phase inverter. I'm just making the audience to think about. You have a three-phase inverter, right? And an inverter means a conventional three-phase inverter do have 6 switches. Okay, why means the upper switches are named as 1, 3, and 5, and the lower switches are named as 4, 6, 2. Right? So this is the switching. This is the convention of naming the switching sequences actually. Okay, so means 0 is a voltage state. 0, 1, you know, means for see here how this 0, 1 and all these sequences came actually. You know that whenever you have a three-phase inverter and you want to have a valid voltage state in a conventional three-phase inverter, out of the 6 switches, 3 switches must be on in order to have a valid voltage vector space, right? Right. So how many different combinations are possible? 6C3 combinations are possible, right? Fine. Out of those 6C3 combinations, some of the combinations are illegal combinations. Why illegal? Because suppose in a three-phase inverter, suppose phase A, phase B, and phase C, or might be you can say phase R, phase Y, phase B, right? If you take phase RYB, is this naming. In phase R, you have the switch 1 and the switch 4. Upper switch is switch 1 and the lower switch is switch 4. And each and every leg acts like a single pole double throw switch. Okay, either the upper switch can be on in a phase or the lower switch can be on, right? Right. But if suppose means out of this means out of this 6C3 number of combinations, 6C3 number of combinations, if suppose in one combination you have in R phase both the switch 1 and the switch 4, means the upper switch and the lower switch, both the switches are on, it will create a short circuit across them, right? Right. So that's why this is an illegal combination. If you say suppose the switching sequence 1, 4, 6 is an illegal switching combination. Likewise, 1, 4, 2, this is also an illegal switching combination because in one phase, both the switches are on. In one particular phase, if both the switches are on, it will result into an illegal combination. So, four types of such illegal combination can happen due to one phase, due to R phase. Means 1, 4, 3 illegal, 1, 4, 5 illegal, 1, 4, 6 illegal, 1, 4, 2 illegal. 4 such type of illegal combinations are possible. Likewise, if in Y phase, suppose you take, suppose Y phase is having what? Switch 3 and switch 6. I feel so. If I imagine the inverter, then the Y phase will be having the upper part, the upper switch is switch 3 and the lower switch is switch 6, right? So you can say, if suppose you have a switching sequence just like this one, 3, 3, 6, 2 illegal, 3, 6, 1 illegal, 3, 6, 4 illegal, 3, 6, 2 illegal, 3, 6, 5 illegal. Means 4 such type of combination again are possible. So likewise, for the B phase, you have the upper switch is 5 and the lower switch is 2. So you can say, if suppose the switching combination 5, 2, 1 is there, that is illegal. If suppose the switching combination 5, 2, 6 is there, illegal. If suppose the switching combination 5, 2, 4 is there, illegal. If suppose the switching combination 5, 2, 3 is there, that is also illegal. That means what? For one phase, there are 4 illegal combinations possible. So how many legal combinations are possible? How many legal switching combinations are possible? 6C3 minus 12. 4 into 3 is 12, right? That is equal to 8. 6C3 minus 12 is equal to 8. Now, out of those 8 legal combinations, if suppose in an inverter, all the three upper switches or all the 3 lower switches are on, that means if suppose 3, 5, 1 means 1, 3, 5, that is your null state. Means what? The upper leg of the inverter is being shorted actually. That will result into null voltage, means 0 voltage and out. Likewise, if suppose you are 6, 4, 2, all the 3 lower switches of an inverter on, it will also result into 0 voltage. But that is not illegal. That is your null state. So out of those 8 legal states, 6 are active states and 4 are 2 are null state, right? So you can say that I was discussing about that how you can eliminate this pulsating torque by using PWM. Means one of such technique is by using suitable PWM techniques. There are different types of PWM techniques available. Okay, different types of torque pulsation removal techniques are available, but I mainly have worked on reduction of torque pulsation by using suitable PWM technique. Why? Because why I have used this one? Why I have used PWM techniques to minimize the torque pulsation? Because this is probably the simplest way to do it. Why simple? Because nowadays we have different types of DACers. We have D-Space, we have your microcontroller chip, we have your PIC microcontroller, we have your DSP processor, okay, LM series actually, DSP processor. Okay, in our NIT, means in very specifically, we have your 1104 D space DAC card. Okay, now? Okay, so there are different types of DAC cards available nowadays. And thereby, we can design the whole PWM scheme in MATLAB, and then we we just integrate it with the DAC card to get the suitable PWM pulses. It's very easy to derive PWM pulses nowadays because of the invention of different types of low-cost DAC cards. Some people do use Adreno also. They are floating point and fixed point DAC cards. Okay, but floating point do have certain advantages, and fixed point DAC card is having certain restrictions actually. Okay, now the thing is that why I have used, this is the main reason why I have used suitable PWM technique in order to reduce the torque pulsation. You can go through my papers actually. Okay, there you will observe it that I have reduced the torque pulsation by using suitable PWM techniques actually. Fine. Now, how is it possible? How is it possible to reduce the torque pulsation by using suitable PWM technique? In PWM, we have the simplest one is your sinusoidal PWM. Another PWM is a current hysteresis controlled PWM. Another PWM is a selective harmonic elimination based PWM. And the other one is a space vector PWM. Okay, now? Okay, but there is a huge scope in the space vector PWM. Nowadays, I mainly focus on inventing different types of advanced space vector PWM in combination with different types of bus clamping PWM sequences. Okay, now, so in one lecture, actually, it's very difficult to tell what I have done actually. Okay, but bus clamping PWM is probably nowadays the most efficient type of PWM. Why I am saying just a very simple thing I am telling you. Why this bus clamping PWM is very useful, because bus clamping PWM results into minimized switching loss. Minimized switching loss. Why? Along with the reduction in torque pulsation and your means your line current ripple minimization, it also results into best performance in terms of reduction of switching energy loss. It reduces a significant amount of switching energy loss actually. And if the switching energy loss is less, then thereby you can say that the heat sink element requirement is also becomes less. The necessity of use of proper cooling techniques also probably will reduce. Okay, so here means the heat dissipation from the switch is less. That means what? That the overall system will be very much robust. Right now, because one of the major key points of this robustness is your dissipation of heat. If the dissipation of heat is low, and moreover, you know that in vehicular applications, switching energy loss plays a pivotal role. Plays a very important role. Why? Because these inverters or the converters used in a vehicular system are operated at a very high switching frequency, right? In some order of kilohertz, 10 kilohertz, 5 kilohertz, or something like that. And the switching frequency is very high. Switching frequency high means what? In one particular, suppose in 1 second, if the switching frequency is very high, in 1 second, the switches of the inverter will be turned off and turned on quite a several numbers of times. And if the switches in the converter are turned on and turned off several numbers of times, the more you turn on and turn off the switch, the more will be switching loss, isn't it? That is the basic concept of switching loss. That is the basic concept of switching loss. Why? Because see, losses in a switch are basically of two types. The first one is a conduction loss, and the second one is a switching loss, right? So if the switching frequency increases, the losses will also increase. If the switching loss will also increase. And bus clamping PWM are very useful for the reduction of switching energy loss. Why? Because conventional PWM do use 0, 1 to the means. Okay, I'm not going into that part because that means those things are not there in my slides actually. So it's very difficult for me to explain those things. So this is your techno-commercial comparison of EVs in present in Indian market. There is Nissan Leaf, there is Mahindra Verito, e-Verito also we can say. There is Tata Nexon EV. So these are the main, means major companies which have till now produced EVs under Indian market. And this is the specification, the specifications. Okay, most of the, you can see that most of the market means most of the commercially available EVs do use induction machine either or permanent magnet synchronous PMS, majority of them. Okay, and as Debasis had told that in future he feels, or I do also feel, that synchronous means a switched reluctance machine will be the major one. It will suppress the induction machine as well as the other machines, so because of its inherent advantages. Okay, BLDC is also often used for scooters actually. Okay, but for four-wheelers, mainly induction machine, majority, nearly about 48% of the electric vehicle companies do use induction machine. Okay, and nearly 32% or something like that. I can't remember the numbers right now, the exact number right now, but it is somewhere near to 32% of them do use permanent magnet synchronous machine. But as because the control topologies of switched reluctance machine is not yet developed to that extent, that's why switched reluctance machine till now it is under the stage of research. In industries, till now it is not used to that extent. But near future, people are doing a lot of research in it. Okay, so in near future, SRM will find its potential application. But in scooters, electric scooters, brushless DC machine mainly is mainly your hub type or inner cell type, your BLDC machine are basically used. Okay, because of its simple structure. Okay, and as because the brushes are not there, so the brush drop is also absent, and thereby you can see it's very useful for the two-wheeler. But for the majority of the three-wheelers in Indian market, or you can say abroad, even Tesla also use induction machine. Tesla is the major one actually. Worldwide, you can say Tesla is the major one. Okay, so this is a techno-commercial comparison of EV present in the Indian market. Okay, now let's come on to means I have said that, means along with Debasis sir also said that one of the main reason of why the induction machine is mostly used in different industries, means your commercially available electric vehicle, is probably due to the maturity of its control technology, right? Okay, you can easily control the speed of the induction machine by using different control techniques. Okay, so the first one is your vector control, and then after I'll come to the direct torque control, right? The first one is your vector control. Vector control, you must have learned, I mean, you must be knowing this thing. Still, I will just recapitulate. I will just tell these things. Okay, vector control is that. Just wait for 1 second. Induction machine control can be of two types. The first one is a V by F control. The second one, of course, can be a vector control, right? Okay, the second one is, of course, is a vector control. Just wait for 1 second. Let me take some time to take the screenshot actually. So this is okay. So let me take the screenshot. Abhijit, Abhijit. Finish. Okay, fine. So now let's come to the control topologies of an induction machine, right? Sorry. So there are two types of control techniques available for an induction machine. The first one is a V/F control, but I said that V/F control is not good for a low speed application, because in low speed, you'll be saying that it will ultimately result into field weakening or flux weakening mode of control, and thereby you need an extra boost converter. Okay, but for high speed application, so that means but for high speed application, V/F control is good, but vector control is probably the best one. Vector control was first being invented most probably in the year 1969 by the famous scientist F. Blackie. What he did is that this control topology is very simple actually. Okay, in this machine, see, vector control can also be called as your trans-vector control, perfectly decoupled control, or there are different names, means field-oriented control also. FOC means field-oriented control. FOC means field-oriented control. There are different names of it. Okay, so in any kind of control topology, your main objective is to control the speed of an induction machine, control it in such a fashion. Suppose in some point of time you want your induction machine to run at a speed of 850 RPM. Just for an example, I'm saying under Indian road condition, it's very important to have a perfect control topology of whatever motor you are using in electric vehicle, because the motor used in electric vehicle must have a unique capability to adapt the speed requirement. Why? Because it must be capable of withstanding the intermittent nature of the load. What is the intermittent nature of the load again? Suppose in Indian road condition, we have huge traffic actually. Okay. Furthermore, the road is also not smooth. Okay. The road is also very much hostile, full of your potholes, full of mud and something else. And furthermore, the inclination of the road is also very high, especially in northeastern region, especially Arunachal Pradesh. The road inclination is very high. So if you dream to drive an electric vehicle in Arunachal Pradesh or any other hilly region like Sikkim and all, your vehicle needs to have a very robust controller. Fine, na? Fine, na? Why? It forms an intermittent nature of the load. That means what? You want frequent escalation and frequent deceleration. Furthermore, another important point is that in foreign countries, the drivers driving the electric vehicle do drive very smoothly. They don't do like certain फटाक से speed को बहुत बढ़ा दिया या फटाक से speed को बहुत कम कर दिया. It doesn't happen. But in Indian road condition, most of the drivers do drive under drunken condition. Sometimes they drive very fast, and suddenly when they see a dog or might be cat or might be human being coming in front of their vehicle, they suddenly intend to stop it very fast. They apply brake. That means what? The driving pattern of the driver is not also appropriate. That's why, in order to make electric vehicle very much suitable for Indian road condition, it's very useful, it's very vital to have a robust control topology of what type of machine you are using in the electric vehicle. Okay, so that's why there is a need of devising a robust control topology, robust drive system or powertrain system, whatever you say. Okay, so vector control is one of that type of control. This was being invented by F. Blackie in the in the year 1969, I feel. Okay, so what do? In vector control, we make the machine operate like a separately excited, fully compensated DC machine. You know that the expression of the torque of a separately excited, fully compensated DC machine is equal to K into IA into IF, where IA is the armature current and IF is the field current. Okay, but in induction machine, you don't have IA and IF. But still, you want your machine to operate, means the torque equation of the machine must be such that it will resemble to that of a separately excited, fully compensated machine. You know, if you have performed the DQ axis modeling of an induction machine, you have found the torque equation of the induction machine is somewhat 3/2 P/2 Lm by Lr into IDS into IDS into phi QS minus of ID QS into phi DS, like that. Okay, it is somewhat in this fashion. It's a non-linear torque equation. But somehow, if you can reduce the torque expression into that fashion, you can achieve the goal of controlling the speed of the induction machine in a simple way, actually. Right? So this is what better means. In order to do that, one thing I'm just moving a little bit fast over it because now I'm in means now there is no time. Actually, now it is, I feel, 5 o'clock. Okay, so I will discuss this thing later on, or you can, if you have any doubts, you can mail me, or you can have some question answer session also now. So what you do is that we make the rotor flux of the machine get aligned along the D axis. So if you do that, you will see that phi QR is equal to phi R and phi DR is equal to 0. Sorry, phi DR is equal to phi R and phi QR is equal to 0. Now this phi R can be constant or it cannot be constant. Okay, normally in practical scenario, the phi R varies sinusoidally. What is this phi R? The phi R is the rotor flux. Right? If you do this type of orientation, there are different calculations actually. Okay, you can achieve the goal of making the induction machine behave like a separately excited, fully compensated DC machine. Right? Now let's go to the block diagram of this vector control of induction machine. I am seeing that participation is very low, but that's okay. If you feel like you're not getting any knowledge from this one, you are free to I don't force you to join actually. So see here, this is an induction machine. Right? Now see, if you want your induction machine to be if you want the speed of the induction machine to be controlled in your way, you can't connect the stator winding of the induction machine directly to three-phase winding. No, you can't do it. You will have to provide the supply of the three-phase supply of the stator winding of the induction machine via an inverter. Okay, why via inverter? Because the output of the inverter can be controlled by using suitable PWM techniques. Because the inverter is made up of some sort of switches. And depending upon the switching sequence of those switches, the output voltage and thereby the output current can be controlled. Right? And moreover, you know the torque of the, and thereby you can see the output current and output voltage of the machine is getting controlled. Thereby you can say the torque is getting controlled, and the torque is getting controlled. You can see the speed of the machine also is getting controlled. Right? Right now, so you can say that ultimately you want control over the torque. Right? So this is the block diagram. I'm not going in details with it. Okay, a direct torque control and all these things will be discussed later on, because now it is like 1 hour 12 minutes already. So so now over to the participants. If you're having any questions, you can ask me. I'm not going in details for the direct torque control, speed sensorless vector control. You know these things actually. I hope initially I felt that I would make up to the presentation, but now the time is very less. And moreover, the number of participants are also very low. Now it is 56. So I feel the participants are also not interested to listen this so many things and all. So do you have any questions? You can raise it.
Sir, why we cannot go DTC always? Generally, most of the people are using FOC or vector control.
Yes, direct torque control actually now one of the main reason is that see direct torque control. If you know the DTC actually, you'll be seeing that you need to form a switching lookup table, right now switching lookup table. Okay, and in direct torque, see direct torque control is advantage. This one was first being proposed by ABB. Direct torque control topology was first being proposed by ABB. Okay, and this is a very good control topology. Frankly saying, why it is good? Why it is better than? Why this direct torque control is better than vector control? One of the most reason is that one of the main reason is that direct torque control doesn't require any coordinate transformation block. Coordinate transformation block means what? This one, ABC to DQ and DQ to ABC. Path transformation and class transformation block is not required. And thereby, the memory requirement also becomes less. That's true. Okay, now, and moreover, it's a very simple topology. But direct torque control is a very new one. And the main thing is that if suppose you want to change the converter topology, suppose in place of a normal three-phase inverter, we want a neutral point clamped inverter. Then the switching lookup table will also change, and this will be very complex. Because inside the means your hexagonal state, there will be different many subsections actually, subhexagons. Okay. So if you want to control, or suppose if you want to employ a flying capacitor type of inverter or different types of multi-level inverter topology, you will see that the switching lookup table will become more and more complex as you increase the number of levels of inverter. But again, nowadays we need to have minimal line current ripple. And thereby we need to use different multi-level inverter topologies, because we know that if you go on increasing the number of levels, the line current ripple will also go on decreasing. But again, if you use direct torque control on the multi-level inverter concept, the switching lookup table will be very, very complicated. But nowadays, most of the people, even Tesla also, to use this direct torque control topology. Okay, it's not true that direct torque control is not being used. And moreover, people are going for your speed sensorless control, means model reference adaptive control based. Because the speed encoder actually do give a lot of errors. And if you can estimate the speed properly, there is one of the modern innovation is there is Kalman filter based state observer. Okay, so there are different types of model reference adaptive schemes which are being used nowadays actually. Though these schemes are not yet used in industries, most of the people do use your FOC or DTC or this type of control scheme. But in coming years, I feel that MRAS based control topology will actually drive the market, because it is so precise. Nowadays people are using Kalman observer also do have different categories actually. Okay, so near future MRS will be the key one, because elimination of speed encoder is the major one actually. We need to eliminate the speed encoder. I feel I have satisfied you actually.
Yes, sir.
Okay. Anyone else from participant side? Anyone? You can ask me in the chat box also. How to open the chat box? How to open the chat box? Chat, yes. My voice is not audible.
Very much audible, sir.
Okay, very much audible, na? Okay. So anyone? See, this presentation will be good for the electrical background means participants, faculties, but those who are from mechanical, there will be a little bit problem for them. Yes, please tell.
Sir, you explained about the usage of three-phase motors.
Hmm.
Uh, uh, Still, we are in Indian railways. They are using a single
Traction. Yes. In traction, actually, this is a beautiful beauty actually. In traction, we do still use which one? Traction, we do use single phase one actually.
Yes, sir.
Okay. In traction motor, we do still use single phase one in traction drive. Okay, I will discuss this one. Okay. Actually, in traction, this three-phase one is not that much suitable. Why it is not suitable? There's specific reason behind it. Okay, I can't remember it right now actually. In traction drive, I'll have to just go through it once. I forgot it actually. Right now, I can't remember it right now. Sorry for that one. Okay, because I don't see. I have a tendency of not bluffing actually. Okay, I
Okay,
will
sir. Okay.
give the answers whenever I am perfectly sure
Yes,
about it. But I know
sir.
that
My
this traction
question
drive.
is, sir. My
Hmm,
question is not towards
hmm,
that one.
hmm,
You explained about the effective usage of three-phase induction motors in drives.
Yes.
But where we are lagging in transporting the direct induced electrical energy to the motors in vehicles.
Induced electrical energy means please repeat it once, sir. Please
So
repeat it
because
once.
we are having only a one option to use the stored energy in battery. That makes us to think of the inverter simultaneously. But when we touch into the industries, they are having bus bars to collect the electrical energy and drive the
Yes.
hoist like those applications directly.
Yes, that is your vehicle to grid application. Okay, V2G actually. Okay,
Yes,
that is
sir.
different. Okay, in V2G, yes, V2G is also now a very much researched area. Okay, but the thing is that most of the industrial means your most of the commercially available vehicles. Okay, they are most of them are battery operated, and moreover, one of the advantage is that nowadays, means electric vehicle, we don't use that huge tubular battery structure actually. We don't use it. Nowadays, we use bottom battery actually, lithium ion bottom battery actually. Okay, so the battery infrastructure is also increasing day by day. So hopefully, yes, V2G is also a very good option actually. Okay, I admit it. But battery operated electric vehicle, due to the invention of different types of battery structures, okay, and battery price is also getting lower day by day. So that's why battery operated electric vehicle is also a good one. But the problem with that is that if the battery after some period of time, the battery will not be that much efficient, and we'll have to exclude that battery. So that part will also pollute the environment. Okay, and
Okay, sir.
moreover,
Thank you.
your use of this renewable energies means your photovoltaic. Suppose I seen it. I have seen it like 3-4 days ago. Actually, Tata has proposed an electric vehicle where the rooftop of the car will be totally installed with a solar panel. Okay, now so now people are going for this one, for this renewable energy integrated electric vehicle. Okay,
Okay, thank you, sir.
so did you understand what I was trying to
Yes, sir.
say?
Yes, sir.
Was
I
this
get.
session helpful at all?
Yes, sir. Yes, sir. I get some clarity on your answers.
Thank you. Okay, then tomorrow we'll be having your yoga session. Okay, the yoga session will be hosted by your I feel your art of living. Okay, Pandit Sri to the power infinity Ravi Shankarji. Okay, not him actually. One of his disciple will be operating it. Fine. Thank you.
Thank you.